In this demonstration of FloEFD for NX, we're going to be looking at an IGBT module such as are used in electric vehicles and other high power applications where control of current is necessary. As you can see, we have a fluid region where coolant is passed, and that is used to convectively cool the actual silicon modules on the top there, which are generating a lot of heat. So in this example, we are looking to optimize the design of this base plate to achieve a optimum cooling and pressure drop solution across the whole unit. So first of all, let's have a look and open up the part that we would like to optimize. This is a copper base plate. We can see an arrangement of fins which we have patterned in the path of the fluid itself, and if we go to the tools and expressions section, you can see that we have three user-defined expressions at the top: the diameter of the pins, the draft angle, and the pitch between the pins. And these are three expressions that we're going to be optimizing using FloEFD. We can at this stage also apply a material by going to the More and Assign Materials option, and in this case I'm going to select this body and assign copper and hit OK, and now this part has been assigned copper. So let's save this and go back to the top level assembly and start our FloEFD process. So to start FloEFD, we're going to go to File, All Applications, Simulation, and FloEFD Simulation, or we can start this using the Control-Shift-F option. Now that we're in FloEFD simulation mode, we can first of all check the geometry, ensure that all of the fluid region has been captured correctly and there are no leaks or gaps anywhere inside the model. And by clicking Show Fluid Region, we can see where the software thinks that the fluid region is going to be. You can see there's a couple of extra volumes in here between the O-ring seal there and in the top of the IGBT module, but we're just interested in the main fluid region where the coolant is going to be running. So that's found that successfully, so we're ready to start our FloEFD simulation. So let's run through the FloEFD Wizard. This will set up some of the base parameters for the simulation and is a good place to start. So I'm going to give this a name. I'm going to choose my unit system, which in this case I'm going to have a custom unit system. I'm going to change my pressure to millibar in this instance, because that is the unit that I'd like to measure pressure in. This is an internal analysis. We're also interested in heat conduction in solids. We are not interested in anything else. We're going to leave on this exclude cavities without flow conditions also. Now the working fluid, I'm going to come into liquids, come down to the user defined section and choose my water glycol mixture and add that into my user defined fluid section. New fluids can be created by clicking on the new button as well. My default solid I'm going to be choosing for this model. In this instance I'm going to choose aluminum. I'm going to leave all of these settings and I'm going to change the temperature to 65 degrees C to better replicate the under hood or trunk compartment temperatures. So we click finish, and the first thing we'll notice is this black box around the geometry that indicates our fluid region, and now we're ready to start applying some of the materials and boundary conditions and heat loads onto the model. So let's come over to the FloEFD tab, and we can see that we've got an empty project at the moment. So the first thing I'm going to do is I'm going to scan the NX files for any materials that might be already assigned and add those into FloEFD automatically by using this import data from model option. So we can see the software has found some copper in here. There's also a polyurethane applied onto the rubber seal there, so I'm going to import those, and that applies all those materials for me automatically, along with aluminum for the casing as well. And if I click on any of these materials, we'll be able to see where those are assigned in the model, and those will be highlighted as you click through those. The other material I need to assign is silicon, so let's insert a solid material. I can either click on the screen or I can come over to my NX tree and find the IGBT and diode parts, so I'm just control clicking these parts, add them into the selection dialog. If I zoom in, you can see they've been highlighted in orange in here, predefined, semiconductors, silicon, and OK. And if we look over here, we now have silicon assigned onto these particular components. So the next thing I want to do is apply some boundary conditions for the flow through the unit. So I'm going to just hide my case very quickly, and in FloEFD I can assign a boundary condition up here. So a boundary condition is a way of introducing flow or pressure into the computational domain. So I'm going to choose the internal face of this lid that I've created. This face, the fluid touching face. Choose a volume flow rate of 5 liters per minute, and under the thermodynamic properties I check that we have 65 degrees C applied correctly, and hit OK, and we can see our red arrows there indicating our inlet boundary condition. Exactly the same thing for the outlet, another boundary condition. This time, rather than an outlet flow, we're going to be choosing a pressure opening. A pressure opening is a way that fluid can either enter or leave the system, so we just need a known pressure for the fluid to push against. And I'm just going to choose atmospheric pressure. And we have our blue arrows to indicate the pressure condition. Okay, next let's apply a volume source, and I would like to apply a heat load onto my IGBTs, again selecting them in the tree, and these ones for a total of a 400 watt dissipation on these IGBTs. Okay, that's going to spread those 400 watts evenly across those 6 parts. And in exactly the same way I'm going to insert another volume source, but this time on the diodes. Okay, these are the reverse diodes. Highlight these, and this time we're just going to be 150 watts. Tick OK, and we can confirm that we've got the correct powers on each of the IGBTs and the diodes. Now the final thing that has to be done is the creation of some goals. This is very important for the optimization stage. We can apply a volume goal, and I'm going to choose my IGBT heat source here. That highlights those 6 bodies, and I'm interested in knowing what the maximum temperature of the solid is going to be. And I'm just going to rename this IGBT max temperature, and that will monitor for me what the maximum temperature of the IGBTs is going to be that we'd like to try and minimize. The other parameter that we'd like to try and minimize is the pressure drop of the coolant across my IGBT module. We could just populate this with a lot of fins, ensure we got good heat transfer, but then the pump required to force the fluid through at that flow rate would have to be much larger. So minimizing the temperature and the pressure drop is the trade-off that we'd like to perform. So to do that, I'm going to select and insert a surface goal, monitoring the surface pressure on the inlet. We know what the pressure on the outlet is, so I'm going to choose the average static pressure on the inlet, and let's just call this inlet P. So we have 2 goals now, and the last goal I'm going to create is something called an equation goal. Equation goal simply does a simple mathematical calculation. I'm going to choose the inlet pressure minus the environment pressure that we had on the outlet, add those together and just rename this delta P. So this will give me the overall delta P in the system due to my 5 liters per minute of flow rate of coolant at 65 degrees C across this unit. So this model is pretty much ready to go now, so let's bring back my casing and just confirm one more time that we have got the correct fluid region. This time you'll notice that we've only got the main flow region, we haven't got those small little volumes around the seals. That's correct. We can overlay the computational mesh on the screen and adjust this accordingly, finer or coarser. And then we're ready to hit the run button, where the software will first mesh and then solve the simulation. You can choose how many CPUs you'd like to use during the solve phase, and that will you can also choose closed CAD if you want to free up your NX license, and that will then go through and crunch the numbers either on a local machine or a network machine somewhere else. So let's just hop over to a version where we have some results. Let's now look at some of the results of this particular model. This model takes about 10 minutes or so to actually solve, and let's spin this around so we have the flow coming from the left to the right of the screen. So first of all, I'm going to visualize what the mesh looks like. The mesh is a Cartesian system. As we can see, Cartesian finite volumes within our computational domain, and they're finer where the pins of the cold plate are, and then coarser in other areas. So this is an automatic mesh that we have in FloEFD. So after the mesh, we can have a look at the velocity in the system. So you can see high velocity coming in. As it hits the pin, it distributes and it goes down the various pathways there between the pins. And by zooming in, we can see where the recirculation zones are going to be inside the system and get an idea of what the flow profile through this module looks like. I can also have a look at, for example, the temperature, and if I probe this, we can see our 65 degrees C on the inlet and 67.5 on the outlet, so we can get an idea of the delta T in the system, where the cool areas are, where the warmer areas are as well. We can also, for example, visualize what the pressure loss in the system looks like, and if we auto range this, we can see the delta P across the system. We can also have a look at the temperature of the cold plate. So this shows us the temperature distribution, the hot areas on the back. I can create callouts to show us what the temperature variation looks like, and the temperature on the rear of the unit also. The other thing we can visualize is the heat transfer coefficient. This shows us how effectively the pins are moving heat into the oncoming fluid, and the more red the fins are, the better the heat transfer is into the moving fluid. Bringing back the geometry, we can also see what the flow in the system looks like. This is currently pressure. Let's go back to temperature of the fluid, and we can visualize how the water or the engine coolant moves through the system. If there's any recirculation zones, if there's any dead zones, we can visualize that and perhaps design something in there to better get the flow through the system. Next, we can have a look at the goals, and if I show the three goals that we're interested in, we can see the maximum IGB temperature 97.64, the delta P of the system 7.51, and the delta T of the fluid 1.73 degrees C rise across our unit. And these are the two parameters that we would like to optimize using the parametric study next. Okay, so as I said, we'd like to optimize this pin arrangement, and for that we're going to use the parametric study option. And a new module in FloEFD 18 is this multi-parameter optimization, or HEEDS module, and this allows for more advanced geometry optimization. So here is where I'm going to add in my expressions. So right at the start of the demonstration we talked about the diameter, draft angle, and the pitch that's available for use and optimization, so we're going to add those in. And now I can also define the variation. So I want the diameter to be able to be varied from 2 to 4 millimeters. The draft angle is going to be varying from 1 to 4, and the pitch from 5 to 10 millimeters. Next, move on to the output parameters and choose the goals of interest that we'd like to optimize. So let's come down to the maximum temperature of the IGBT and the delta P of the fluid. A lower temperature and a lower delta P is the best scenario. So there's no target at the moment, so I want to minimize this, and I can weight this accordingly, the importance factor. Okay, and the same with the delta P. Let's minimize that. And finally, we can also define a upper and lower bound for these. So ideally, I want the upper bound of the temperature to be less than 95 degrees C, and the delta P of the fluid, I want this to have an upper bound also of 10 millibar. So again, minimize it, but try and get it below 95 and 10 pressure drop. Moving on to the scenario tab, we can choose the maximum number of calculations. I only want to run 40. There is an optimization algorithm from HEEDS, the weighted sum or the Pareto front. Let's use the Pareto front. I'm only going to choose 10 points to start with. We can choose where the solution will be run, as there will be a lot of solves, how many cores will be used, and what the maximum simultaneous runs is going to be. So with all those set, we can hit the run button, and that will go away and run all of those points for us and give us the optimum solution. So we already have that. Let's jump over to that now and look at the solution. So under the scenario, you can see that all of our points have finished with the varying diameter, draft and pitch. I can come over to the study plots, which will give me a better graph of the temperature, the overall temperature versus the delta P of the system, and there's a few points here which are optimal. So there's 2 points, number 6 and number 30. So this one gives us 8.75 and 94 degrees, 9.59 and 92 degrees. So I'm going to choose this one, point number 6, and of course we can see all the values here as well. Here's number 6, and from here we can click create project, and that will create a geometry variation for us. So let's visualize that now by coming over to the optimum solution, and now this gives us the visual representation of the pin configuration to give us the best pressure drop and heat transfer characteristics based on the input parameters that we defined for this parametric study. Thank you very much for watching this demonstration.